Hello, I'm Victor Brea, full professor at the University of Santiago de Compostela, and we are here at CiTIUS, Research Center on Intelligent Technologies. We are within a summer school funded by Cátedra, Televés, USC, the Microelectrónica, and we have the pleasure to have here today Cory Lammie, a doctor at IBM Research Center in Zurich. Hello.
That's okay. Thank you for having me.
Right. Okay. So the first question is tell us about IBM. What do you do? A general view or introduction of what does IBM in this field of AI and circuits for AI? Could you please?
Yeah, sure. So I'm in the research division of IBM, but the internal mandate within IBM is to basically look at what is next for computing and to realize this vision.
Okay. And what specifically, Cory, does your group do in this regard? I mean, what are your main, let's say, topics of research? And if you could please give us some examples of applications or projects you are running nowadays.
So the group I'm in specifically researches three topics. So the first is using emerging compute paradigms for deep neural network or artificial intelligence acceleration. The second is for neurosymbolic computing. So what neurosymbolic computing is, it's an alternative computing paradigm to standard deep learning, where we try to use different reasoning. And then the third thing that my group is looking into is the device and the material physics to realize the hardware for these two.
So you go from materials to applications?
Yeah, exactly. So we operate over all levels of the
all the hierarchy.
Stack.
Okay,
Yes,
so
exactly.
here at CiTIUS, we cannot cover all the topics, so we are more focused on circuits, like you said, emergent circuits to put on top of the mainstream CMOS, and always for computer vision, or at least this is our main research topic. And so in this regard, we are involved in some European projects related to that. So we are close to each other in a way, so we can interact. Yeah, this is good. So, and how do you see AI nowadays? What would you say are the main barriers for their deployment, for training, for general public adoption of these things? What do you see? How do you see it?
I see two problems or barriers. The first is the increasing size of these models. So especially of recent, these transformer-based models or large language models, for example, ChatGPT, are increasing massively in popularity. But the amount of energy or resources required to train these models and to serve these to their end users is enormous.
Yeah. Could you say that the problem could come from energy? Like, for instance, those huge data centers we all heard about. They demand a lot of energy, a lot of water, a lot of things. Do you think that this could be a barrier? Because apparently, like you said, those models don't stop to grow, and they are more and more complex, and this means a lot of energy. I've heard at some point that the energy they consume, it's like thousands of families for 1 year just for training and things like those. Do you think that this could be a problem? How do you see it?
Yes, exactly. I mean, as we said, the size of these models is increasing at a exponential, or I should say a logarithmic rate. So at some point in time, this will become a huge problem.
Now, from that perspective, what we do is we try to squeeze to reduce the size of the models to put them into embedded device for a person to carry, let's say, in one of their hands. Do you do the same? Do you shrink the size of the models there?
Yes, exactly. So we're looking at two approaches internally. One is reducing the size of the model, so like you discussed. So we have a European Union project on this. It's called NeuroSoc. And the idea here is that we can use these kind of new compute paradigms to implement these models more efficiently in a resource-constrained setting.
Just to clarify, I mean, just to the general public, when we talk about squeeze or reduce the size of the models, the thing is that maybe you can reduce the size of the models. You don't need so a huge device consuming a lot of energy, a lot of space. For instance, if you go for automotive applications, you cannot put there on the car like a big GPU or something like that. And the thing is that we can do that with a very small loss of accuracy, isn't it? What is your experience? I mean, you can squeeze the model, you can shrink the size of the model with, let's say, a very a small price to pay in terms of accuracy. The accuracy decreases.
Yes, exactly. So one of the things we're looking into is to develop a accelerator for these types of models. So specifically for automotive applications, for things like object detection. So like detecting a sidewalk or some kind of crossing in the setting of a car. And we're specifically interested in a power budget of approximately 1 watt.
1 watt. Just for the people who are listening, 1 watt could be, let's say, powered by, let's say, a small battery in a way, like the batteries we have in our mobile phones, so to speak, for some hours at least. Okay, not 700 watts, which is like 100 more times.
Yes,
and
exactly.
This is the power consumed by those big GPUs by NVIDIA. All right, let's move on. So the next question is exactly that. I mean, how do you see the future in the sense that are there any alternatives to NVIDIA's GPUs, or in other words, to Moore's law? What is your view about that? What is the future? Do you see a future where, at least this is what we see here, where you can put together different devices, heterogeneous devices? I would like to know your opinion as an expert.
So maybe first I can cover Moore's law. So I think it's known now that the size of a transistor, at least the size of the circuit, has traditionally halved every decade. But this law is coming to an end because we're struggling to scale these things further. So you're very much correct in the sense that I think we need to look at these kind of alternative options or emerging compute paradigms. And one of the technologies that my group is specifically looking at is referred to as in-memory computing. And the key idea here is that we can take inspiration from the human brain to varying degrees. So for a point of reference, the human brain consumes approximately 20 or 30 watts of power.
Yes.
Compared to these graphics processing units, which consume in the order of 700 watts. 700,
yes. And so the thing is that, do you think that it could be sustainable, Moore's law, even though there is a physical limit, even though the main companies are struggling to go beyond that limit, so to speak, with different techniques? But do you think that it could be sustainable in the sense that it is more and more expensive to fabricate a chip? Recently, ASML came up with this extreme ultraviolet, device to, what do you think? It could be sustainable because, decreasing the size of transistors.
Yes, it's becoming increasingly challenging. So no, I agree that we need to start looking at different non-silicon or these kind of approaches.
Okay, all right. So different devices in a way.
Yes.
And how do you see the thing? Do you think that, because one thing is that people maybe are not aware of that, but when you use artificial intelligence like ChatGPT, what we are doing is to have a prompt, and that prompt is executed distantly far. In whatever data center, we don't even know where the data center is. So the thing is that this is a huge data center, and so you prompt something on ChatGPT, but the execution of that model doesn't run in a closed device. Not in your mobile phone, locally in your mobile phone, but far away. So what is your point? What applications do you see close to you, in the sense that close to the sensor, close to the interaction, or close where the sensor is, in terms of to run one of these models on a mobile phone or on a what they call Internet of Things device, like a sensor in a farm or something? Could you please talk about what is your experience at IBM? Because I can tell you hours, but I prefer...
No, I think this is a very powerful notion of being able to process the data near where it is collected. I think one thing a lot of people don't understand is where their data is sent and exactly how it's processed and who is privy to that information. So there's huge benefit to be able to process data locally in this sense. For example, to have some kind of large language model that might reside on your phone where your data is secure and safe.
Not to mention the privacy issues. For instance, in computer vision, if you have a camera and you want to run an algorithm, maybe if you're a company, you don't want those data to travel along the line up to the data center because there might be privacy issues. This is one of the things we did, or one of the, let's say, motivations behind our missile project, to run something locally with low energy, but also, if you think about it, if you don't have to broadcast images or video, and you can run algorithms locally in your device, you don't have to. I mean, you're not exposed to, to attacks, so to speak. Do you think that this?
Yeah, exactly. No, this is a huge issue.
A huge issue, right?
Yes.
So, okay, so edge computing versus cloud computing. So nowadays there are many research groups, I can tell that, many, European projects running with the same end, with the same goal, sorry.
Mm-hmm.
So, and what about education? Does IBM do anything related to that? Do you have specific problems or specific actions directed to that at IBM?
To attract students or to?
To draw students or just even training activities like, for master students, for graduate students, or of course for PhD students. And
yeah, sure. So we do a number of different activities. So we have quite a strong presence at conferences, and I'm here for a summer school at the moment, where we try present on what we do and encourage others to participate. As far as recruiting PhD students is concerned, we have a PhD fellowship program. So this is actually how I started at IBM. So I did my PhD in Australia. And through this program, I had a mentor at IBM.
All right. There in Australia or?
Remotely. So in Zurich was my mentor,
okay.
Yes.
But of course with a university, because IBM cannot issue the diploma or the title, right? Or
so IBM cannot issue the diploma, but we do have pre-doctoral researchers that are employed at our labs.
Jointly with the university?
Yes, exactly. Okay. So it's always through a university, but the bulk of their supervision is actually done at IBM Research.
Yeah, no, I understand. So, and could you please give us examples? Do you have any university now? Of course, I guess that the ETH at Zurich.
Yeah. So ETH is the main university where a lot of these students are enrolled, but we also have students who are enrolled at the University of Patras and universities in other European countries.
Okay.
Who work primarily at IBM.
So, and how is it? I mean, does IBM, let's say, come up with a topic, or could universities go there and propose, kind of proposal, a joint proposal?
So normally it's done in a joint kind of way, so that the supervisor at the external university does have some input on the student.
Okay.
But I think one thing that's unique within IBM is that the student itself is supervised by a number of different researchers.
Yes.
So in my team specifically, we have a number of tenured researchers who have been there for a long time. So it's somewhat unique in regards to the level of supervision that these students get and access to these different individuals. Whereas in a conventional academic setting, they might have one singular point of contact or a few number.
Yeah, I see. It's like a team?
Yes, exactly.
It's like a team. And how many, related to that, Cory, how many people are you there at your research center at IBM?
So within the Zurich lab, we have around 300 active researchers at any given point.
All right.
So this includes a number of temporary positions, for example, interns and master's students.
So it's possible to do a kind of summer trainee too there.
Yeah, we quite often have internships for many different students.
I see. So this is another way to interact with academia.
Mm-hmm.
Okay, I see. Okay, so you have some education opportunities there and some interactions with academia, which is very interesting. You mentioned before that you were active at conferences and conferences and things like those. Actually, we met at a conference, in a tutorial we gave there at the International Symposium of Circuits and Systems in Singapore, 2024. So there is a question here related to, one thing is, how to say this? I mean, a company is a company, so you have to sell. So the thing is, there is that delicate balance between what to reveal and what not to reveal. So I would like to know, or I would like you to tell us something about how do you deal with open source and patents and things like those. I mean, I'm sure that you have filed patents in the past and maybe you are doing so. Could you please elaborate a little bit on this topic of patents, open source, open publications, things like those? How is the policy you follow?
Yeah, sure. I mean, it's always a complicated issue, as you would imagine. But I think one thing that IBM is doing as a kind of global approach is that we're quite heavily incentivizing at the moment working in the open, or having a directive for open sourcing different projects and code.
This is really interesting because it's very nice. Actually, I have to mention here that Cory gave a tutorial on how to use one of their tools for AI with let's say non-conventional devices or emerging devices, like what they call MEM restores, which is a different device. And actually have to tell people that we use that tool and we are designing circuits and systems with that tool, so which is really good to us. Of course, we are a public institution and we are obliged, and we really want to do it. We really want to make our thing public, our research in terms of code when possible, and also publications. But we also have some patents, and I was asking you the question about patents because we have a spin-off, and very often venture capitalists came with the same claim. You have to have a patent for us to put money into the company, and this is something in a way, how to say that, in a way, it's a contradiction in itself, because if it is a company, the best way to protect your company is not to reveal, at least at the very beginning. But venture capitalists ask us that. I mean, you have to file a patent. So it's a little bit contradictory. So if you are one of those who start up a company, why to reveal those? And it seems that big companies like IBM, are not pursuing patents anymore, or at least not so often nowadays, right?
Yes, so we still do pursue patents, don't get me wrong, but there's a less emphasis on it. And I think one of the reasons specifically for artificial intelligence is that many people have kind of realized that you need to work in the open with these kind of open source tools and develop a community backing. It's very difficult to do these kind of things at scale when everything is closed source or private.
Yeah.
So, of course, certain components of this still need to be private for many different reasons.
Yes.
But I think in the long run, it's beneficial to open source some aspects of these kind of tools and libraries that we develop, such that other people can contribute to them and work on these kind of things. So yes.
Yeah, no, it's a mutual benefit. I mean, for both, for the academia and for industry. In the end, I mean, the information flows in both directions, right?
Yes, exactly.
So, yeah. And, okay, this is an interesting question. And another thing that annoys me about patents is that it takes too long to have the patent approved. Then when the patent is passed, is approved, the thing is that what you did is old. How do you see that? Because the pace is really fast. It's going too fast. I mean, how do you deal with that in Harvard? I mean, models, AI models go too fast. I mean, how can you catch up with that? Because hardware obviously lags behind. It's slower than software, and it takes you more to do things than in hardware than in software. So it might happen, and I would like to know your experience. It might happen that you start with one design focused on a given AI model, let's say convolutional neural networks. But then in 2017 came out that paper, Attention is All You Need, with the famous transformers. So it might happen that you are caught in the middle of a design or of a project. Or how do you deal with that at IBM?
Because... No, this is a very good question. I mean, one of the things that we've learned because of the rapid pace of the different model developments is to try to design hardware that is relatively flexible.
Okay.
So at the moment, transformers are the big thing. There are also now a new emerging class of models referred to as state space models. So it's one of these things that we do need to keep in mind, or are actively keeping in mind, to create hardware that is suitable for what currently is out there, but what may be suitable for other alternative things.
So it means that you have to read a lot of papers too.
Yes, exactly. We need to keep very much up to date on the most recent
You have
developments.
to study. I mean, because sometimes people think that you are in a company and that's it. I mean, you have like a stable knowledge and you don't go beyond that. But the truth is that you have to study every day.
Yes, exactly.
Because every day there are more and more new papers. I can tell you that I'm not able to read all the stuff because there's too much stuff. And I can tell our experience about that. What it happened to us is that we started an European project, but then we saw that there were like the transformers more and more, let's say, adopted by the scientific community, but it was really hard to, to deal with this because you have a PhD student that it's not easy to change, this research line of a person because you are very focused on a given topic and then you cannot change. And related to that, it came to my mind, Cory, how do you think that a PhD is important to your company?
I think so, yes. I mean, at least for the research I do, it is a mandate.
Mm-hmm.
But I agree with you that I think that the conventional approach of researching one particular topic for a long duration, although it may be beneficial in the long term, specifically for these new kind of compute paradigms, is very difficult.
Yeah.
So I think that you have to be flexible and pivot very quickly.
Because one thing is that the scientific field is very demanding in the sense that you have to publish, but to publish, you have to beat the state of the art. But to beat the state of the art is not easy nowadays. There's too much competition in the field of AI. So this is it. But PhDs are valuable to you.
I mean,
like
at
employees.
Least within IBM, one, I think, benefit that we have is that we have a large group of researchers who are quite knowledgeable.
Mm-hmm.
So what I mean by this is that when we're able to tackle a large problem, we can have many people working on this at the same time. So it's much easier in this regard because of the expertise we have.
No, I see. Mm-hmm. What you mean is that there is not one person trying to solve a problem, but there are many minds around thinking about the problem. Yeah, I see. But the way, I mean, the thing that there is only one person, a PhD student, trying to solve a problem is always an added value in the sense that you have to address a problem from a very different perspectives, and this is a valuable knowledge. What I try to point out here is that a PhD is always valuable in the sense that you have to solve a problem, not to mention that you have to develop all your communication skills, like oral, written skills. Nowadays, ChatGPT, it's a little bit different. And speaking about that, obviously you have to write down documents and things like those. Do you use ChatGPT or things like those there for that?
We do have an internal version of a large language model.
Okay, your own.
Yes, exactly.
And so you use it.
Yeah, so we have a series of what are referred to as these granite models.
Okay. Yeah. That's nice. And how do you see the scaling problem of AI? So we talked about that before. So you think that the solution is like a heterogeneous combination, maybe of different technologies? And
so yes, I think there are many different avenues. I think one of the avenues that's been looked at within IBM is instead of making these models larger to attempt to make them smarter. Okay. So this ties back to the neuro-symbolic computing approach. It also ties into if you can reason with these models. So rather than kind of taking a prompt, propagating it through your model and getting the output, you can kind of basically enable the model to get the output and then to do some reasoning based off this in some kind of feedback fashion. Mm-hmm. But I think as far as the hardware acceleration is concerned, it makes perfect sense to look at these alternative technologies. For example, those based on in-memory computing or those that may be brain-inspired.
In-memory computing, by the way, it came up several times in this conversation. In-memory computing, it is this, just to make it accessible to the public. So typically what computers do is that you have the computer unit here and then memory with data far away, let's say from the computer, from the compute unit, and in memory computing tries to bring both of them together for the data not to travel so long, because to travel or to lead data from one place to another takes energy.
Yes,
right?
Yes, that's perfect. I mean, it often takes more energy to transmit or to move this data between the two locations rather than to actually process it once it's there.
Yeah. And can I ask you a question? Because I know the answer, but I would like to know your opinion. So because the cost of the chips is becoming higher and higher. So one thing is, because people, the public maybe, knows about those technology nodes of TSMC, the Taiwanese semiconductor manufacturing company, which is the biggest one with Samsung, as far as I know. Maybe you can correct me, Cory. And they are very advanced. They have very advanced technology nodes and 2 nanometers, which is very, 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 very small. So, but the thing is that if we are a company and if we want to design chips, if we want to tell them, hey, fabricate those chips for us, that would cost...
Yes, exactly.
Millions or...
So maybe I can go back to the Neurosoc European project that we have. So what we're looking at is a processor for autonomous vehicles. And what we're specifically looking at here is actually using larger technology nodes or ones that are cheaper, so it's better for the end consumer.
Okay.
So it's not necessarily always better to use a more sophisticated technology to create these kind of accelerators.
No, and I think that I will end with this question because this is related to what nowadays is happening in Europe with the Chip Act, in the sense that maybe governments are obsessed with the fact of bringing here a very advanced, foundry with very advanced technology nodes, but this costs more than 10,000 millions of euros. I mean, the foundry itself, but maybe it's too much. What is your view? And let's finish with this about that. Your personal opinion.
No, I think this makes sense, and it is expensive, and that these specifically low technology nodes, so 4 nanometers, 3 nanometers, 2 nanometers, make sense in some specific applications. But that being said, I think having the infrastructure required to manufacture chips at this specification is extremely important.
Not to mention the human resources to run, let's say, the foundry, right?
Yes, exactly. I mean, it's an enormous investment, and I completely understand this. But I do think it is required if Europe wants some independence.
I see your point. Yes. For, let's say, for a data center and for our own, let's say, high-performance computing resources like the Barcelona Supercomputer Center.
Exactly.
Just to mention one of them here in Spain.
But this being said, I enormously agree with you that for a vast majority of applications, I don't think anything this sophisticated is required. And I think it may make sense to use a larger technology node or one that is cheaper to manufacture.
Yeah, for instance, a sensor to detect fire or something. Okay, I think that with this we are done. So we really thank you, Cory Lammie, doctor at IBM Zurich. And we really thank you for having you here.
Thank you.
Because with this, we end. I think we're done. And this is all. And I hope that you all have enjoyed this really nice talk and conversation with Cory Lammie. Thank you all.